Hey everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. In this video and the next one, we will give use to all of those quantities we have derived in previous videos. We will treat energy applications. Today we will introduce energy state diagrams, and after that we will analyze what its derivative means and also what its critical points are. So let's start! Great, now let's introduce energy state diagrams. For this, we will use an example. A ball that is on the top of a dome, a circular dome for simplicity. This is going to have a radius r, and this is going to be our initial state, and we consider a final state after some time has passed, in which we have our same dome, but our ball is no longer over here. Our ball is going to be at an angle theta. We are going to choose our potential zero energy point to be this one. Note that as we are considering gravity near the surface of the Earth, this is the potential energy graph. This is a graph of the potential energy. However, we are going to express it for simplicity in terms of our angle theta. At theta equals 0, our potential energy is going to be equal to U theta equals 0, it's going to be equal to mgr, because it's the height at which the ball is. For our case with an angle theta, we are going to have that our potential energy over here, over U theta, it's going to be the height of this. And in this case, it's going to be r cosine theta times mg. We will assume that there are not non-conservative forces. So we know that the change in mechanical energy equals 0. That means that the change in potential energy plus the change in kinetic energy equals 0. And at the start, we don't have any kinetic energy. So this is going to be our final potential energy minus the initial one plus our final kinetic energy minus the initial one, which is 0. In this way, we can find which velocity is the ball going to have for each angle theta in a very easy manner. We just need to solve for it, and we get that the kinetic energy, not the velocity. And this is an example where we can use these energy state diagrams with our object in a state and another state, and we also indicate its potential energy and its kinetic energy really mean. Now we will understand how to complete these diagrams to also include kinetic energy in the following segments. Before introducing that notion of combining kinetic energy and potential energy in the same energy state diagram, we first need to understand what the derivative of the potential really is, of this energy state diagram really means. So we know that the change in potential, x final minus u x initial, it's no other thing than minus this work integral. So now that we know this, let's assume for a second that we are dealing only with x hat direction motion. So this is going to be minus xi to xf times f dx. We know from calculus that uxf minus uxi equals the integral from xi to xf of du. And we can multiply this by dx over dx and make it equal to xi over xf du dx dx. And now, by equating these both sides, we find that the things inside the integrals need to be the same. And we conclude that force equals minus du dx. In general, in 3 dimensions, we can generalize this to force being equal to minus the gradient of potential energy. Let's see this in an example. Earlier, we found that potential energy for a spring was 1/2 kx squared. By applying this formula, we should find the formula for the force in a spring. If we differentiate this and put a minus sign, we'll get minus 1/2 k, and that is 2x. So we can cancel this 2 with this one, and this is indeed equals to the force, which is minus kx. So it actually makes sense. Furthermore, I want you to realize one thing about this. We have said in our earlier videos that gravitational potential energy and all of the different types of potential energy aren't really defined. They are defined up to a constant. So we could add a plus z over there. However, that z, as I said, it's a constant. It doesn't depend on the parameters of the system. That way, if we differentiate over x this expression instead of only this, that constant is going to vanish and it's not going to affect the force. This is a very insightful thing about potential energy, knowing that if you make a graph of potential energy, the slope of this graph is the force that an object will feel. Great, now let's connect these energy state diagrams, these graphs of the potential energy with kinetic energy. Imagine we have no non-conservative work. That is that work, well, that's not a W. Work non-conservative equals 0. In that case, we know we're going to have a mechanical energy equal to a constant. So we can draw that value in this diagram. Let's say, for example, that our value is over here. This is the value of the mechanical energy. And we're going to draw it as a line because it's the same for all x. So it's not a pretty good line, but you get the idea. We're going to have some points, as we see here, that all the mechanical energy is going to be potential energy, because recall that the mechanical energy is equal to the potential energy plus the kinetic energy. Therefore, at these points, all of the mechanical energy we have, it's going to be potential energy. At that point, we'll call it A. And at this point, that we will call B. However, at some points, such as this one, we are not going to have any potential energy, and therefore the mechanical energy is going to be completely kinetic. We see that the kinetic energy, I keep confusing the terms, it's going to be equal to these lines over here. The difference between these two functions, and that can easily be seen in math as kinetic energy equals E mechanical minus U. So what we understand is that in these graphs, the slope is going to be the force, minus the slope. Therefore, this means we're going to have a force over here, a force over here. It's going to be smaller, 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 till we reach over here where it's at the smallest value, and then it starts going in the opposite direction. It grows, but then it stops being too large once more when we reach this point. So these two are important points, we can see, and then it starts growing once again and becomes really, really big very fast. Just so you know, this is the equation we are dealing with for some A and B. You can find it as an exercise if you want to. The thing is to know that for x equals 0, we need to have a critical point, derivative equals 0, and it's also equal to 0. And you can find those constants easily if you want to. So, we see two very different types of critical points. We have this point over here, towards which the arrows point. You see, all of these arrows from here to there point towards this critical point. So that means this is a stable critical point. Stable. Because if you start, that's not a B. Because if you start close to this critical point, you are very likely to stay over there. Well, you aren't likely, you are going to stay over there. However, this point is completely different. You have some arrows pointing in that direction and the other arrows pointing in that direction. Therefore, this point is going to be unstable. And at the point itself, you are not going to move. However, if you are a little bit to the right or a little bit to the left, you will end up moving at some point. There is a third type of critical points that are called semi-stable, and they have this form. And they are a ladder, kind of a ladder. And you have some forces that reach over here, and then they continue. Now, I want to understand a little bit more what this kinetic energy over here really means. So, what we see is that a ball that starts at this position, or really at any point along this graph with the corresponding kinetic energy, can move to all of these points of the graph that are permitted by this energy. However, all of the other regions are forbidden for a ball that starts in this position. But we see that if we start increasing this mechanical energy until we reach this point, for example, what we find is that there's a point at which the kinetic energy is so large the ball can go away from here and pass this unstable critical point and continue to go down. So these energy state diagrams including kinetic energy, give us a sense of the regions towards which an object that starts with a given initial conditions can reach. And it also tells us the kinetic energy an object is going to have at each point of the x-axis in this case. That is all for today. I hope you gained a more deep understanding of how you can use energy principles to your advantage with energy state diagrams. In the following video, we will use these tools to solve some problems that are very hard with Newton's laws of motion, but with energy they are simplified greatly. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!